lecture we revisit integer programming. In the previous lecture I had actually wound up the course with a treatment on quadratic programming. Now we are going to revisit integer programming, largely due to some feedback that I have received and the need to look into integer programming algorithms in little more detail. In earlier lectures we had seen 3 algorithms for integer programming, and these 3 algorithms are the Gomori cutting plane algorithm, the all integer dual algorithm, and the all integer primal algorithm. In addition to these 3 algorithms, we have also seen branch and bound algorithms to solve integer programming problems. A typical integer programming problem would look like this. It will have a maximization or a minimization objective. It will have a set of constraints. All decision variables xj will be greater than or equal to 0, and in addition we restrict or constrain the decision variables also to integers. So when one or more of the decision variables take integer values, then it becomes an integer programming problem. And in this example, both the variables x1 and x2 should take integer values, and therefore it is an all integer programming problem where all the variables have to take integer values. If we have situations where some of the variables alone take integer values while the rest of them can take continuous values, then such an integer programming problem is called a mixed integer programming problem. In the earlier lectures we have covered all the algorithms that we have covered so far, which are these 3 and the branch and bound. They have all been covered for the all integer programming problem where all the variables were restricted to be integers. Now in this lecture and in continuing lectures we will also look at algorithms that address mixed integer programming problems in addition to addressing or revisiting the all integer algorithms that we have already seen. Now if we see this classification, I have written the Gomori cutting plane algorithm, all integer dual and all integer primal algorithm on one side and branch and bound on the other. The reason being these 3 come under a very generic category of what are called cutting plane algorithms, and branch and bound is a separate class of algorithms to solve integer programming problems. The essential difference lies in the fact that at every iteration we add one constraint which is called a cut in a cutting plane algorithm, add a constraint to the existing solution and then solve it again. In a branch and bound algorithm we essentially divide the problem into 2 by adding constraints of the type xj greater than or equal to lj or xj less than or equal to uj, creating 2 problems from an existing node and then finally trying to get the best solution among a set of problems that have been solved. Whereas in the cutting plane algorithms at the optimum there is only one solution, and that optimum solution is reached by adding cuts sequentially to an existing solution. So let us go back to these 3 types of cutting plane algorithms, and we also observe that the cuts that we have seen earlier are different for each type of the algorithm. So what we will do is we will simply revisit the problems that we have done, try and redefine the cut, and then try and address a question: is there a generic expression for a cut? Can we have something called a fundamental cut from which each of these cuts can be derived? So we will do a derivation for a fundamental cut and then show that each of these cuts can be derived from the fundamental cut under certain problem conditions. And then we will also revisit a few things as to the significance of how we get the all integer dual cut and the all integer primal cut. So let us go back to the example that we have already seen. We have used the same example in the earlier lecture when we did the Gomori cutting plane algorithm as well as the all integer primal algorithm. We used a different example for the all integer dual algorithm. The all integer primal algorithm essentially requires a maximization problem with less than or equal to type constraints and non-negative or positive values on the right hand side. So such problems can be solved comfortably using an all integer primal algorithm, irrespective of the objective function, whether it is maximization or minimization, irrespective of the type of constraint, the Gomori cutting plane algorithm can be applied. So we had used this example to explain both the Gomori cut as well as the all integer primal cut. Now before we actually get into the derivation of the Gomori cut, let us also try and understand how a cutting plane algorithm works in general. So if we have a general integer programming problem, let us say, now let us say it is an integer programming problem with two variables x1 and x2. Now let us assume that these are the integer points. Let us say the LP optimum is somewhere here. Now let us assume that the LP optimum is here. Please note that this is not the graphical representation of this problem. This is a different problem. Here I am just trying to draw a graph to explain a feasible region of a linear programming problem as well as an integer programming problem. The feasible region of the integer programming problem contains only the set of feasible points which are here. For example, a point here is not feasible to the IP, assuming this is 0, 1, 2, 3, 1, 2, 3 and so on. So let us say if the objective function is like this and moves in this direction, this will be the LP optimum for this linear programming problem, and one of these will have to be plus, of course, have to be the optimum solution to the integer programming problem. So in a cutting plane algorithm, what we essentially try to do is to try and introduce constraints which are in the form of cuts, such that these cuts or constraints remove a certain area from a feasible region, assuming 2 dimensions, or assume certain space from the feasible region for higher dimensions. And then at the end of it, when we continue to solve LPs, at the end of it, the LP optimum will be an integer solution. So that is the fundamental idea behind a cut. For example, one could have a cut like this. If there is a cut which is like this, which takes away this place, and then when we solve a corresponding LP, now let us assume this will be the integer optimum solution. So the purpose of the cut is to keep chopping off or keep removing areas from this, such that at the end of it a counterpoint solution to an LP will be an integer point. Now we have already seen in earlier lectures that the cuts are slightly different for the Gomori cutting plane algorithm, for the all integer dual algorithm and the all integer primal algorithm, but essentially they do the same thing of trying to remove areas from this feasible region, such that as you add these constraints and keep solving LPs, at some point the LP optimum will be an integer solution and it will also be integer optimum. Now this also implies that the cut that we enforce or add into this does not eliminate or remove any integer point from the feasible region. So that is another thing, that every cut has to ensure? The cut has to ensure that on addition of the cut, no integer feasible point becomes infeasible after the addition of the cut. The cut should satisfy all the integer feasible points in this region. So, when we generate a cut, we keep that in mind, that no integer feasible point becomes infeasible with the addition of the cut. So, one of the rules which we have to follow is to ensure that the cut does not take away any integer feasible point from the feasible region. So, we will keep this in mind, and then we will revisit how we created a Gomori cut from this. Now, let us go back to the problem that we have already solved using the Gomori cutting plane method. Now, this is the LP optimum table that we have already seen in a previous lecture, using a slightly different notation for the simplex algorithm, and we have already seen this notation also in the earlier lecture. So, this is the LP optimum to this problem. So, the LP optimum has x1 equal to 28 by 9, x2 equal to 133 by 45, and the objective function value is 273 by 45 or 91 by 15. Now, what we have done is we have solved the linear programming problem, which means we have left out this integer part, and we have just solved the problem up to xj greater than or equal to 0. We already know that if the LP optimum has integer valued solutions, then it is optimum to the integer programming problem as well. But now the LP optimum is not feasible to the IP, because both x1 and x2 have fractional values. So, 28 by 9 and 133 by 45, which are not integer values. So, we have to now solve the integer programming by adding suitable cuts. So, when we worked on the Gomori cut, we followed a simple principle whereby we could either frame a cut based on this row or x1 row, or we could get a cut based on the x2 row. Now, we followed a general guiding principle that we will generate a cut from a row or through a variable that has the largest fractional component. So, the fractional component of this is 1 by 9, this is 3 plus 1 by 9. Fractional component of this is 43 by 45, this is 2 plus 43 by 45. So, this has a larger fractional component, and therefore, we said we will get a Gomori cut out of this. So, let me spend a couple of minutes once again explaining the Gomori cut, so that we also understand the context of the Gomori cut when we derive a general expression for a cut. So, we go back and rewrite this. We rewrite this as x2 equal to 133 by 45 minus 4 by 15 x3 minus 7 by 45 x4. So, this is the equation which is represented by this. So, we rewrite this equation in such a manner that the variables are on the left hand side and the constants are on the right hand side. So, this would give us x2 plus 4 by 15 x3 plus 7 by 45 x4 is equal to 133 by 45. Now, the right hand side is written as an integer plus a positive fraction less than 1. This is always positive. So, this is written as 2 plus 43 by 45. Now, because this is an all integer algorithm with all coefficients integers and the right hand side integers, x1 and x2 have to be integer valued at the optimum. Therefore, the slack variables x3 and x4 that we have introduced, which are here, should also have integer values at the optimum. Therefore, this is an integer, this is not an integer, this is not an integer, because we have a fraction multiplying x3 and a fraction multiplying x4. So what we do now is we keep this as it is. If there is an integer, we keep this. The coefficient here happens to be a fraction less than 1. So we retain it as it is. If the coefficient were a number which is positive and greater than 1, then we write this as an integer plus a positive fraction less than 1. For example, if this were 24 by 15 x3, this would have been written as x3 plus 9 by 15 x3. If this were 47 by 45 x4, this will be written as 1 plus 2 by 45 x4 or x4 plus 2 by 45 x4. Integers are written exactly as integers. Now the next question is, what happens if you have negatives? If this were minus 4 by 15 x3, then this has to be written as an integer plus a positive fraction less than 1. So if this were minus 4 by 15 x3, this will be written as minus x3 plus 11 by 15 x3. If this were minus 7 by 45 x4, this will be written as minus x4 plus 38 by 45 x4. So this should always be written as an integer plus a positive fraction less than 1. It turns out that there is the integer component is 0 and the positive fraction less than 1 is 4 by 15 here. So it is written as 4 by 15. Similarly, this is written as 7 by 45. So now what we do is we keep the same thing again and then we try and look at the left hand side as well as the right hand side. So this is an integer, this is non-integer, this is an integer, this is a fraction less than 1, strictly less than 1, fraction strictly less than 1. This is an equation, therefore at the end of it this value should be equal to this value, which also means that this at the end of it, if it has a fractional component, then that fractional component has to be equal to 43 by 45. At the same time, this is an integer, this plus this should have a fractional component of 43 by 45, but this can be 1 and 43 by 45 or even 2 and 43 by 45, it can be anything like that. So this portion alone can be an integer plus a positive fraction less than 1, and it will be a, if it is, it can either be a positive fraction less than 1 or a positive integer and a positive fraction less than 1, because this is a positive coefficient, this is a positive coefficient, these two have to be greater than or equal to 0, therefore this quantity cannot be a negative quantity the way we have written it. That is the reason we wrote this as a positive fraction less than 1. So this can be either 43 by 45 or 1 and 43 by 45 or 2 and 43 by 45 and so on. So we write this as 4 by 15 x3 plus 7 by 45 x4 is greater than or equal to 43 by 45, because this is either 43 by 45 or 1 and 43 by 45 and so on. So this is essentially the Gomori cut. Now we make this as an equation by adding a negative slack. So this will become 4 by 15 x3 plus 7 by 45 x4 minus s1 equal to 43 by 45, from which take s1 to the other side. So s1 equal to minus 43 by 45 plus 4 by 15 x3 plus 7 by 45 x4. So this when on writing will become minus 43 by 45 minus 4 by 15 and minus 7 by 45. So this is your Gomori cut. A simple thumb rule to write the Gomori cut is, when you are generating the cut out of this, take the fractional portion, put a negative sign and write it minus 43 by 45. If this is positive, take the positive fraction less than 1 and write a minus. So positive, take a positive fraction less than 1 and write a minus. For example, if this were 24 by 15, this will become minus 9 by 15. If this were 57 by 45, this will become minus 12 by 45. If this is negative, then do the complement, in the sense, if this is minus 4 by 15, then this will become minus 1 plus 11 by 15, therefore this will become minus 11 by 15. If this were minus 7 by 45, it should be written as minus 1 plus 38 by 45, so this will become minus 38 by 45. So either one can go through these steps and then write the Gomori cut, or we can simply write it this way. So this is how the Gomori cut was written. So let us revisit the all integer dual cut, which we have done earlier, and we will go back and derive a general expression. So let us go back to the all integer dual cut and see how we derived the first all integer dual cut, and that comes from, we consider a different example here. We have not used the same example in an earlier lecture, we have used a slightly different version of this example in the earlier lecture. So we set up the initial table, so this will become, we add x4, x5 and x6. So we would start with x4, x5 and x6, and we would have minus x1, minus x2 and minus x3 here. This, we are going to use an all integer dual algorithm. So an all integer dual algorithm implies that the dual is feasible and the primal is infeasible. So this will become 8, 4 and 6, dual is feasible, primal is infeasible. So minus 18, minus 4, minus 3, minus 6, minus 15, minus 2, minus 3, minus 5 and minus 20, minus 9, minus 6 and minus 3. Another way of doing it is, one could say that 4x1 plus 3x2 plus 6x3 minus x4 is equal to 18. So take x4 to the other side, so x4 is minus 18 plus 4x1 plus 3x2 plus 6x3. We already have a minus here, so you get all these negative terms. So if we go back and see how we derived the all integer dual cut, what we did was, we started by looking at the variable that among the negatives, the one that is most negative was taken as the source row. So the cut is generated from this row, the x6 row. So if we revisit the all integer dual algorithm, this is the source row, and then we look at all, how many of these have negatives, all 3 of them have negatives. So we go to the corresponding value 8, 4 and 6, and then the smallest one, we keep this 8, 4 and 6 here. The smallest amongst them is 4, so divide by 4 and take the lower integer value. So that would give us 2, 1 and 1. Now take the positive values of this 9, 6 and 3, find out the ratio. So you would get 2 by 9, 1 by 6 and 1 by 3. So take the 3 values 8, 4 and 6. So we have the values 8, 4 and 6, let me write it here. The smallest among them is 4, so divide by 4 and take the lower integer value. So you get 2, 1 and 1, 1 comes because 6 by 4 has a lower integer value of 1. Now write the corresponding numbers here with a positive sign. So 9, 6 and 3. Remember we have considered only those that are negative. So write them with a positive sign. Now divide them to get 2 by 9, 1 by 6, 1 by 3 and take the minimum of these. So 1 by 6 is smaller than 1 by 3. Now 1 by 6 is 3 by 18, 2 by 9 is 4 by 18. So the minimum is at 1 by 6. So take 1 by 6, multiply the source row with 1 by 6, take lower integer values and write the cut. So your cut will become S1 variable 20 by 6 or minus 20 by 6, lower integer value is minus 4, minus 9 by 6, lower integer value is minus 2, minus 6 by 6, lower integer value is minus 1, minus 3 by 6, lower integer value is minus 1. So you have generated the all integer dual cut and then you leave this variable out, this is the leaving variable and this is the entering variable. Pivot has to be minus 1 in an all integer dual algorithm and these two are, they have a pivot of minus 1. Amongst all those that have pivot of minus 1, pick the one which has the smallest value of the dual, therefore this is the entering column, this is the leaving row and one could do the iteration for the all integer dual algorithm. So now we have seen the way two cuts are generated, we have seen the way the Gomori cut is generated here for a different problem, we have also seen the way the all integer dual cut is generated. So now let us ask a question, is there a general way by which we can tie up all these cuts and have a single formula or a single mechanism by which one can generate these cuts? So we try and solve that using we try and address that using a small derivation which I am going to do now. So let us assume that xi is equal to b naught minus sigma aij xj summed over j. Now essentially there is a source row from which we are generating the cut. If we look at a Gomori algorithm, this is the source row, the row that has the largest fractional value. If you look at the all integer algorithm, this is your source row, the one that has the most negative value amongst the infeasible values. So the source row is written in this form. In fact, when we wrote the Gomori cut, that is exactly what we did, we first wrote the source row. So this is a variable xi from which we are going to generate a cut. So in this case it will be x2 equal to b naught is 133 by 45, the aij xj are these 4 by 15 x3 and 7 by 45 x4. So you can write the source row this way, where b naught is your right hand side, the xi is a basic variable that is expected to be an integer, right now it is infeasible. So now what we do from this is multiplying by h not equal to 0, multiplying by h not equal to 0, it is an equation. So we could have sigma h aij xj plus h xi is equal to h b0. So I am bringing the aij xj to the other side. Right now h is not equal to 0, it is an equation, so h can even be negative, but later we are going to have only positive values of h. Now since all xj greater than or equal to 0, we can now write this as absolute value of h sigma aij xj this can be written as lower integer value of h into xi plus sum over j h aij xj is less than or equal to h b naught. Now let me explain this, this is not very difficult to follow. Right hand side is the same, so the right hand side has not changed. Now I am taking this h out and writing the lower integer value. So this term can only be less than this term. Similarly, I am taking the lower integer value of, sorry, this is the corresponding term, so this will be less than this. This is the corresponding term, so this will be less than this. So the LHS here will be less than or equal to the LHS here. The right hand side is the same, therefore we convert this equation to inequality. So this will be less than or equal to h into b naught. Now this should be an integer because all xi's and xj's are integers. This is a lower integer value of h, so this is an integer multiplied by another integer. Similarly, this is an integer multiplied by another integer. So the left hand side is an integer, and therefore this has to be less than or equal to the lower integer value of h into b0. This already holds, so all you do is take a lower integer value of this, therefore this will also hold. Now we call this as equation 1, we call this as equation 1 and we call this as equation 3. So equation 1 into lower integer value of h minus equation 3 would give us sigma So let us see how we get this expression. So multiplying the first one by h, which means you are taking this to the other side. So multiplying this by, so absolute lower integer value of h into aij comes from here, minus this comes from here, I am subtracting. So this part is fine. Similarly, I have lower integer value of h into b0 coming from here and hb0 coming from the other one, and since I am subtracting, one is an equation and the other is an inequality, so the sign gets reversed. So this will be greater than or equal to absolute value of h into b naught minus hb naught. Now this is called a fundamental cut. This is called a fundamental cut. So depending on the values that you give to h, the cuts will change, and most importantly what we have taken care of in this is that every integer feasible solution will satisfy this cut. No integer feasible solution will be violated by this cut, by the fundamental cut, which is a very important aspect which we understood when we were actually looking at the graphical representation of the problem. So we have to ensure that all integer points satisfy the cut, and they will, the way the cut has been written, they will satisfy. Now different values of h would give us different cuts depending on the algorithm that we are using. So now let us try and look at the Gomori cut from this. Now when you look at the Gomori cut from this, you realize h is equal to 1 will give you the Gomori cut, h equal to 1 gives you, will give you the Gomori cut. Now how do we check that? The Gomori cut that we wrote from here to this, the Gomori cut was actually 4 by 15 x3 plus 7 by 45 x4 is greater than or equal to 43 by 45 is the Gomori cut. Now go back to this expression, B naught is 133 by 45. So this is 1. So this is 133 by 45 minus lower integer value of 133 by 45, which is 2. So 133 by 45 minus 2 is 43 by 45, which comes here. Now go back to these, then you realize that this is Aij minus lower integer value of Aij. So the fractional portion was 4 by 15. So 4 by 15 minus lower integer value of 4 by 15 is 4 by 15. Therefore you got the 4 by 15. Similarly 7 by 45 minus lower integer value of 7 by 45 is 7 by 45, because lower integer value is 0. So you got this. So whenever, that is why we use this, whenever this is a positive fraction less than 1, it automatically gets the negative sign. If this were 24 by 15, then it would have become 24 by 15 minus lower integer value of 24 by 15, which is 1, and 9 by 15, which is what we would have done with a minus sign. So this is the left hand side. If it were a negative, if this were minus 4 by 15, then this will become minus 4 by 15 minus lower integer value of minus 4 by 15. So this would have become minus 4 by 15 minus 1. So minus 4 by 15 plus 1, 11 by 15, which would have come as a negative sign as 11 by 15. So the left hand side of the Gomori cut comes from this, with h is equal to 1 would directly give us the Gomori cut. Now other values of h will suitably taken would give us other cuts. Now if we actually observe this and see what we do here, we used in this case h is equal to 1 by 6. If you remember, right, this is the value that we used. So let us try and substitute 1 by 6 and see whether we get this cut. Now what happens when you use h is equal to 1 by 6? Lower integer value of 1 by 6 is 0. Therefore what happens? This will go, this will remain, this will go, and this will remain. B naught was minus 20. So you got B naught is minus 20, you got minus of lower integer value of minus 20 by 6. I hope we are doing all right. B naught itself is minus 20. So minus 20 by 6 has a lower integer value of minus 4, with a minus sign would give us a plus 4, which later on substitution would give us this minus 4. Or when we move to the other side of the equation, you will get that value. So this does not exist. When h is a positive fraction less than 1, this term goes, this term also goes. Now similarly you can see that in all of these, the lower integer value of h into Aij is the one that remains. Now the Aij values are minus 9, minus 6, minus 3, h is equal to 1 by 6. So lower integer value on multiplication is exactly what we did. So minus 9 by 6 has a lower integer value of minus 2, minus 1, minus 1, and that is how the cut is formed. So in this particular example, the cut comes from using h is equal to 1 by 6. In a similar way, we can actually explain the all integer primal algorithm, and the corresponding primal cut also is something that we can easily explain, which we can also do it for a moment. So if we were to apply the all integer primal algorithm to this, the table will look like this. We would add x3 and x4. So we would start with x3 and x4 here, and we would have minus x1 and minus x2 here. This is a primal algorithm. So dual will be infeasible, primal will be feasible. So we would have got a minus 1 and a minus 1 here, and then this will become plus 7 and plus 7 here. So x3, So this will become 7x1 minus 5x2 plus this. So this will become 7x1 minus 5x2 plus x3 equal to 7, x3 equal to 7 minus 7x1 plus 5x2. So therefore this will become 7 and minus 5, this will become 12x1 minus 12x1, sorry, so there is a minus here, minus 12x1, so minus 12 and 15. So if we applied the all integer primal algorithm, the most negative of this will enter first, dual infeasible. So the most infeasible dual will enter, in this case both are equal. So we could either start with x1 or we could start with x2. So let us say we start with x2, if we start with x2, then we go back and say there is only one source because there is a minus sign here, there is only one source. So this is your source, so your theta is 7 by 15, which is what you have. So what you do is 1 by 15 multiply with 1 by 15 and take lower integer value. So this will become 7 by 15's lower integer value is 0, minus 1 and plus 1. So in this case h will become 1 by 15. Now once again we can go back and show that h is a positive fraction less than 1, therefore this will go, this will also go. So we will simply have lower integer value of h into b naught. Now this is 7 by 15's lower integer value is 0. Similarly h into aij's lower integer values keep coming. So there is a different h depending on the all integer primal algorithm and another h depending on the all integer dual algorithm. So this is how we can relate the three cuts that we have already seen to what is called a fundamental cut. So another aspect that has to be looked at is this aspect that we did here. Now this needs to be explained further. Even though we were able to get h equal to 1 by 6 and show that h equal to 1 by 6 when you apply this to this cut gives us this particular all integer dual cut, we certainly have to explain a little bit about why do we take these numbers, why do we divide this by the smallest of these values and then go back and divide by these fractions. So that needs a little bit of explanation and let us try and do that. So right now what I am going to do is I am going to take out all of these. I am right now going to leave this, so we are only going to have this the original problem that is represented in the simplex table. Now we need to add a cut which is called an all integer dual cut. Now what do we want? Right now the way this table is written in the all integer dual algorithm, this is a minimization problem with all positive coefficients, all constraints of the greater than or equal to type. So perfectly amenable for the all integer dual algorithm. A simplex table will give you a dual feasible and a primal infeasible solution, which is what is shown here. Primal is infeasible, dual is feasible. Now assuming that we are solving LPs, linear programming problems, what do we want? We want at the end a simplex table where these are positive or non-negative, which means primal is feasible as well as dual is feasible. So any dual algorithm, number one is we want to maintain dual feasibility. So first one is any dual algorithm should maintain dual feasibility. But even before that it is an all integer algorithm, so we want to maintain the all integer nature of the algorithm. So let me say the first thing that you want to do is to maintain the all integer nature of the algorithm. Second thing that you want to do is to maintain dual feasibility. third thing that you want to do, after all the purpose of doing this is to ensure primal feasibility. At some point some primal becomes feasible, only then at the end, at the optimum, we will have the optimum having both primal as well as dual feasible. So we need primal feasibility. And fourth of course is we want the objective function to increase or decrease depending on whether it is maximization or minimization. We want a large increase or decrease, so we are concerned about the objective function also. These are the four things that we want to do. Now the way the simplex table works, the way this particular simplex table works, now let us simply write this cut for a moment, assuming h equal to 1 by 6. So this cut will be -4, -2, -1, -1. Now when we do an iteration of this, what are all the things that are going to happen? We also said this is the pivot. Pivot row is divided by the pivot element, therefore this will become positive. Pivot is -1, so when the pivot is -1, when you divide every element of the pivot row by the pivot, the integer character of that row is maintained. The pivot column becomes divided by the negative of the pivot, so the pivot itself is -1, so you are dividing it by +1. Not only is this integer character maintained, this one remains as positive, which is what you want. So an all integer dual algorithm will have a -1 as a pivot. Having -1 as a pivot helps us in the following ways. One is this term will become positive, this term will remain as positive, and the all integer nature of the table will be maintained, because the only place where you divide are this row and this column. Every other place is only addition, multiplication and subtraction, and therefore the integer characteristic will be maintained. So the pivot has to be -1 in an all integer dual algorithm. So in an all integer dual algorithm, the all integer character is maintained when the pivot is -1. At least one of the primal variables becomes positive when the pivot is -1. So now we have to do few things. We also need a pivot equal to -1, and then we have to find out that h. We have to find out that h, in this case h is equal to 1 by 6, such that I get a pivot equal to -1, plus I have to maintain dual feasibility. Now this -1 at the moment gave us feasibility here. It has not ensured the feasibility of this and this in the next iteration. So h has to be such that that feasibility is ensured, and h should also take us to a reasonably large increase or decrease in the objective function, so that we move towards the optimum. So h has to be sufficiently chosen so that all four are achieved. Right now what we have seen is a -1 pivot would help us comfortably achieve these two. Now h should be chosen in such a manner that the pivot is -1, plus we also achieve these two. Now let us go back to this and see, for example, what are the ways by which we can get a pivot of -1. Now a very simple thing is, if h is equal to 1 by 9 or less than 1 by 9, we will get pivot equal to -1. For example, if we do h is equal to 1 by 9, from these numbers, the biggest of them is 9, the smallest of them is -9. So 1 by 9, h equal to 1 by 9 would definitely give us a -1 here. So if we use, let us use h is equal to 1 by 9 to get a cut which is S1, -20 by 9 which is -3, -1, -1, -1. So this comes with h is equal to 1 by 9, but please note that we have not used h is equal to 1 by 9, we have used h is equal to 1 by 6, because we did not use 1 by 9, we wrote 2 by 9 somewhere, the 2 came because of this 8 by 4, and then we compared 2 by 9 with 1 by 6 and said 1 by 6 is smaller. But right now 1 by 9 could also give us a cut. Now this cut is meaningful if it satisfies all 4 of them. Now we will check in the next lecture whether h is equal to 1 by 9 is able to do that, and why we have chosen 1 by 6 instead of 1 by 9.